Okay. Welcome to CADEPS. Today we have Éric Delaygue, who is going to talk about an Abel's problem and Gauss congruence. Okay, please, Éric.
So thank you very much for the invitation. So it's a joint work with Tanguy Rivoal from Grenoble, and I will talk about Abel problems, and as we will see, Gauss congruences will occur in this problem. So the structure of the talk is the following. So first, I will say some generalities on Abel's problem, which concern, in fact, differential equation of order 1 with an algebraic function as coefficient. And we want to know when the solution is algebraic. Then I will focus on the hypergeometric case and speak about Golyshev prediction on this case. I will give an arithmetic characterization of Abel's problem in terms of congruences. And then I will give a sketch of the proof of the main criterion. So first, let me present Abel's problem. So we are looking for algebraic solution of a linear differential equation. And we start with a differential operator, so k is number field. And we have coefficients, which are rational fraction with coefficient in k, the ai. And being given this differential operator, we can consider the Riccati equation, so which is a nonlinear differential equation of order 1 less than the one of L, and such that y is a non-zero solution of the first operator L, if and only if u, which is the logarithmic derivative of y, is a solution of the Riccati equation. Then we have the following fact about algebraic solution of L. If you assume that L is irreducible, then the differential equation Ly is 0 as a full basis of algebraic solution, if and only if you can find an algebraic solution eta of the Riccati equation, which, so this is the first part, and you also ask that eta is the logarithmic derivative of an algebraic function. So in fact, you have an equivalence. You have to find an algebraic solution of the Riccati equation, but this eta is also defining a first order linear differential equation, which is y prime is equal to eta y, and which has a non-zero algebraic solution y. Okay. So this last equation and the fact that it has an algebraic solution is Abel's problem, and so it's why Abel's problem occurs in such a problem, which is to find a whole basis of algebraic solution to a given differential equation. And the references about all these ideas, this is ideas from Penlevé and his student Boulanger. Okay, so we are interested in the following question. This is being given the differential equation, when does it have a full basis of algebraic solution? Okay. So we can reduce this problem to 3 steps. Okay. The first one, as we said, the first result was valid if L is irreducible. So you have to reduce your problem to the case where L is irreducible, okay? And you have a procedure given by Singer in 1979, which are the one to reduce to the case where the operator is irreducible. Then you consider the Riccati equation, and so the first step is to know if there is an algebraic solution to the Riccati equation. And again, we have a procedure which was given in the same article by Singer. And finally, now if you know that you reduce to the case where L is irreducible, you know that you have an algebraic solution to the Riccati equation. And now you want to know whether being given this algebraic function eta, if now the differential equation y prime is equal to eta y admits a non-trivial algebraic solution. In that case, so you have a full basis of algebraic solution to the first equation. Okay, and this last step, the third one, is called Abel's problem. It was a reference as Abel's problem by Boulanger. And to answer this third step, you have algorithms which are different one, but one by Risch and one by Baldassari-Dwork. I will talk about the one of Baldassari-Dwork later. Okay. So let's see a few examples of solution to this simple equation. One thing, so we consider such an equation with eta an algebraic function, and our goal is to decide whether the solution is algebraic or transcendental. I just give a really simple trick to quickly know that something is transcendental. That when you have an algebraic function, it has moderate growth at infinity. This means that in fact you can find a non-negative integer n and an angular sector s at infinity, such that the algebraic function y is holomorphic on S, and you have the following limit. Okay. So it will quickly discard the fact that a function is algebraic. So for example, you take the above equation y prime is y, so you know that the solution is exponential, and this one we know that it's transcendental, but simple way to do that is that it has not moderate growth, okay, at infinity. Let's take another example. So we take eta equal to x, and in this case we found the solution exponential of x squared divided by 2, and again it is also transcendental. Okay, so now look at an algebraic example. So we take eta is 1 over 1 minus x, and in this case you will find again that y is 1 over 1 minus x, which is rational, so algebraic. And now you take the square of eta, and in fact again y is transcendental. It is exponential of this, and just because it has not moderate growth, you can easily see that it is transcendental. Okay, so we shall see that in fact the fact that eta is 1 over 1 minus x gives something algebraic is easy it's easy to see that eta has to have this particular shape. Okay, and it comes from the first analytic observation. We will look at Puiseux expansion of algebraic function. So to do this, we use the Newton-Puiseux theorem. Okay, so we start with y an algebraic function and delta a point. Okay, and we know though by the Newton-Puiseux theorem that y admits a convergent Puiseux expansion in a slit disk of center delta, and which is given as follows. So in the first case, you consider that the point is finite. Okay, so you have an expansion where it starts at n equals r, but here r could be a negative integer. Okay, then you have coefficient a n, and the expansion now is not like a Lorentz series, but this is with power in n over d, where d is a positive integer, a fixed positive integer. Okay, so you know that if y is algebraic, and then you can expand y like this at the point delta, and you have another formula, expansion at infinity. We won't use it in the talk, but you have also this expansion. Okay, so the coefficients are complex number a priori, and just taking this, you take an expansion at 0, so you have y which expands like this. Okay, and then we will look at the derivative of y. So first, we rewrite y like this. So we want a sum that starts at n equals 0 rather than n equals r. So you have this expansion. And now we will differentiate y. So differentiating y, we obtain this formula. Okay. So now I will also expand with a sum which starts at n equals 0. So we obtain this. Okay. And being given these two formula, I will look at the quotient of y prime over y. So why? Because I want to look at the particular expansion which are allowed for eta. So now I look at this quotient, and we see, just because of the above formula for y and y prime, that we have something like this, okay, which starts because we have a cancellation of these two terms, okay, which just gives something on 1 over x, okay, and so finally we have something like this. But this is algebraic because the quotient of algebraic function is algebraic. But now we see, in regard of the Newton-Puiseux theorem, that in fact this is a special, really special expansion. Okay, so this is an expansion which in fact start at n equals 0. Okay, and so we see that for the equation for Abel's problem to have an algebraic solution, eta must be of a specific form. Okay, so this is the first analytic observation, and it will suffice to solve the rational case. In fact, so the case where eta is a rational function. So in this case, I start with eta a rational function, and I still consider the equation y prime is eta y. And if it has a non-trivial algebraic solution, then we can apply the Newton-Puiseux theorem to the quotient y prime over y in each point of P1. Okay, and if you do this by the same trick as before, you will in fact obtain that eta must be of the following form. Okay, so a sum of beta I over x minus alpha I, where the alpha and betas are complex numbers. Okay, so if you have a solution to Abel's problem, so in fact eta must be of this really particular form. Okay, but then if you have this, you see that the solution, you can write the solution quite easily. And y is a product of the x minus alpha I to the beta I. But now, you know that for y to be algebraic, if you again use the Newton-Puiseux theorem, it will imply that in fact the exponent beta I must be rational, okay, rational number. So that being said, we just found a criterion. Okay, so the solution of Abel's problem for rational function, if you take eta a rational function, then the first order differential equation admits non-trivial algebraic solution if and only if eta is of the above form, but the alpha are complex numbers, but the betas are rational numbers. Okay, so in this case, in fact, everything is known. Okay, so now let's go back to the general case where eta is algebraic, and we make an algebraic observation, and this is the following. So you take eta to be an algebraic function over kx, and y a non-trivial solution of this equation. Then you find that y is algebraic over kx if and only if there is a positive integer m such that you have m times eta, which is the logarithm derivative of an element which is on the field generated by eta over kx. So this is algebraic characterization, and to prove this, you have the following ideas. So for the if part, if you have this relation, if you have a positive integer m such that m eta is nu prime over nu, then in fact you easily find that y is c times nu to the 1 over m, and so that y is algebraic. Okay, so this is the simple case. But for the other sense, so in this case, you know that y is algebraic, and you want to prove that such an integer exists. Okay, so since y is algebraic over k of x, okay, it is also algebraic over k of x eta, and you consider the minimal equation satisfied by y on this field. And then the trick is that you will differentiate this minimal equation. Okay, so I will just write quickly. So let's say I have an equation like this. Okay, and if I differentiate this, so I will have something like this. Okay. And the thing is that now, since you know that y prime, so you will use this, y prime is eta y, so that in fact you can replace there each y prime by eta y. So you will obtain this, okay, and etc. And in fact, all the derivative of y disappear, and so you will have a new equation. Now you use this new equation in combination with the first equation to cancel, for example, the leading part. Okay, and then you will obtain a shorter equation, which will contradict the fact that here you have a minimal equation. And so to not contradict this, this means that in your difference of the two equations, all the coefficients must be 0. And in fact, writing this down, you will at the end obtain something like this. Okay. Okay. So we have this algebraic characterization, and in fact, with the same argument, if you work a bit, you will find that if y is algebraic, then its minimal equation over kx eta is of the form ym plus mu, with mu an element of the field. Okay, so ym plus mu is 0. So this is, in fact, y is the nth root of an element of the field kx eta. Okay, and okay, so you see that in fact y. So you start with the algebraic function eta, you extend the field of rational function kx with eta, you obtain kx eta. And now, when looking at the solution of y prime is eta y, to not extend again the field, in fact, this is equivalent to say that m has to be 1, okay? And this condition for m to be equal to 1 will occur later in the talk, which is one of Golyshev prediction in the hypergeometric case. Is why I focus a bit on this situation. Okay. If we go back to the rational case, so when eta is a rational function, in fact, one can show that m is the least common denominator of the beta. Okay. And at the beginning, I mentioned some algorithm to decide in a finite number of steps whether Abel's problem has a solution or not. And the algorithm proposed by Baldassari and Dwork is based on this algebraic characterization, and so try to find if such a positive integer exists or not. And this is done by geometric considerations on the curve associated with the algebraic function eta. Okay, so now let us see the hypergeometric case. And first, I will give some definition of generalized hypergeometric series. So we start with many parameters. So we have R parameters, the alpha I, which are rational numbers, and S other parameters, the beta I, which are rational numbers, but which are not non-positive integers. And we consider the following series, okay, where you have a product of alpha I, programmer symbol of the alpha I at the numerator, and the beta I as the denominator, and the programmer symbol, which is also known as the rising factorial, is given like this. So an, this is a times a plus 1 up to a plus n minus 1, if n is a positive integer, and this is 1 otherwise. Okay. So this is not conventional writing for generalized hypergeometric series. You will often see in the literature things like this with factorial n there, n, okay? But in fact, if you choose one of the alpha I to be 1, okay, it will cancel the 2, and so this is an equivalent formulation, okay? Okay. So one example, if you take just one parameter at the top, alpha 1, and beta, which is equal to 1, then you find this algebraic function. Now, if you take this parameter 1/2, so 2/1 at the numerator and 2 1s at the denominator, you find this elliptic integral, which is transcendental. And a famous example also, if you make a suitable choice of the parameter, alpha and beta, and a suitable choice of a constant, a rational constant c, you have this example, which is given by a quotient of factorial ratio. Okay, so this is the series expansion of a quotient of factorial ratio, which is known because this quotient of factorial ratio occurs in the proof of Chebyshev on bounds for the number of prime number less than x. Okay, and in fact, this series was shown by Rodriguez-Villegas to be algebraic of a very large degree relative to the parameters. Okay, in fact, the parameters alpha and beta will have denominator which are bounded by 30. Okay, but the degree is really large. It's quite surprising. Okay, and in this talk we will also focus on a particular subclass of hypergeometric series, which are factorial hypergeometric series, so which are really like the later one, which we can express as the generating series of factorial ratio. So we say that a generalized hypergeometric series f with parameter alpha and beta is factorial if you, in fact, can find a rescaling, so given by a constant c, which is a non-zero rational number, and if you can find positive integers, e and f, such that after rescale f, you find the generating series of quotient of factorial ratio. Okay. So to know whether this is possible or not, given some parameter alpha and beta, you have a combinatorial criterion, which is that f is factorial if and only if, in fact, this rational fraction has coefficient in Q. Okay. So, in fact, okay, this is a really compact criterion, but in fact, if you take just a quick example, which is not really sufficient to explain everything, but if you take something like this, so the generating series of this quotient of parameter symbol. So here you easily know that this is not of a factorial hypergeometric series. So why? Because the rule is that if you have 1 over 3, then you need to have also at the numerator 2 over 3. And in fact at the same power. So it's okay at the power 2, you need to have 2 over 3 at the power 2. And in fact, you also need always to have something like this, r over d at the same power for all r which are prime to d. Okay, and so in fact, all this situation is nicely encoded by this, even if sometimes it's not really clear. Okay, well, for example, if we take our second example like this, you can find the rescaling of f. So given by c is equal to 16, and you obtain the following formula, which ends by the generating series of a nice factorial ratio. Okay, so this one is factorial. So now we look at Golyshev's prediction. So according to Zagier, who wrote an article in 2018, Golyshev made the following prediction, and this is based on the theory of motives. So if you start with a factorial hypergeometric function, which is also algebraic, and there is x, so we have x eta there, just because as we see, so we have this, the factorial, let's say that the coefficient of the hypergeometric series are given by this sequence, okay? So as we see, that this is regular at 0, okay? But we already saw that, in fact, if you want that the Abel problem has a non-trivial algebraic solution, you will have something which starts at n minus 1, equal minus 1. So you can't really take eta to be an hypergeometric series, but rather this, okay? Which, so it's it's the same thing to say that x times eta is hypergeometric. Okay. So we start now with x times eta, which is hypergeometric, algebraic, factorial. Okay. Then the prediction was that, in fact, Abel's problem has an algebraic solution, and we have even more that, in fact, y is again in the field spanned by x and eta over q. And this means that, in fact, m is equal to 1 in the algebraic characterization we saw previously. So if we reformulate this, in other words, if you take the generating series of a series of factorial ratios, the QEF, and if you assume that this is algebraic, then in fact, the solution of the differential equation is given by the exponential of this integral, okay? You can rewrite this as x times exponential of this power series, given by the coefficient are q over n. And the prediction of Golyshev is that this is again algebraic, and that in fact, it belongs to the field spanned by x and f. Okay. And Zagier proved the first part of Golyshev prediction, that is that Abel's problem has an algebraic solution, okay, in this family of examples, okay. So given by these three examples where the parameter E and F are such that E is larger than F, okay. And it was made by explicit computation on each of these three examples. And so we give a characterization with Tanguy Rivoal in the case of hypergeometric series. So you start with x times eta, which is an algebraic hypergeometric function. So not factorial a priori, okay? And then in fact you have an equivalence which says that the Abel's problem has a non-trivial algebraic solution if and only if x eta is factorial. So this means that the prediction of Golyshev is sharp. Okay, if you're not factorial, in fact, Abel's problem has no algebraic solution. Okay. So to do this, we used an arithmetic characterization, which I will explain now, and which is based on Gauss congruences. So in the following, we write ZP like this for the localization of Z at the prime P. So equivalently, this is the ring of rational numbers A over B, where B is not divisible by P, okay? And we say that a sequence with value in Q satisfies Gauss congruences for the prime P, so a given prime P, if we have such congruences. So the difference between A of n, P, and an is divisible, in fact, by n and P, okay? So it belongs to n and P, and so it is equal to n times P times a rational number, which has not P in the denominator, okay? There is another way to write this congruence. So this is the following. To ask that for every S and every M, you have such a congruence, okay? And in fact, because in the above congruence, we doesn't look at the divisibility of n by p, okay? So here, in fact, you can think that m is not divisible by p. Well, yeah, and it's the reason why you have two equivalent formulation, okay? So the second one is we find it more often in the literature than the first one. Okay, so if you take a sequence with integer coefficients, not just rational, but integer, then you have an equivalence, which is it satisfies Gauss congruences for every prime p, if and only if, in fact, for every non-negative integer n, you have such congruences. So the sum for d which divides n, and then you have the Möbius function there, okay? And this is congruent to 0 modulo n, okay? And n is just not a prime, it has to work for every integer, non-negative, okay? So why do we look at this congruence? Because in fact, this congruence was proved by Gauss. For a particular case, the case of an is a geometric sequence, r to the n, and first when R was a prime number. Okay, and later it was extended by many authors and independently to the general case where R is an integer. Okay, so it's why these congruences are named Gauss congruences. So in the following, we say that being given a sequence, which is eventually indexed on the relative integers, we say that it has a Gauss property if it satisfies Gauss congruences for all large enough prime p. So because just before we define Gauss congruences for a fixed prime p, and now we ask for a sequence to have such congruences, but for all large enough prime p. Okay. In this case, we say that it has Gauss property. And we also need to consider special expansion of algebraic function because we are not able to consider other field at first. And we start with eta, an algebraic function over Cx, and finite point, delta. In fact, we also can consider delta infinity, but for the talk, I will just focus on delta point in C. And we write is Puiseux expansion at delta. So this is like this, where R is possibly negative integer, okay? And a priori, the coefficients Pn are complex number. We will say that in fact this Puiseux expansion is rational if all the coefficients Pn are rational, okay? So our criterion apply for this particular case of algebraic function with rational Puiseux expansion. So we have the following characterization. You start with eta, which is an algebraic function over Cx, and which has a rational Puiseux expansion at some point. So you find a point where you have a rational expansion. And let's say that the coefficient reads Pn. Okay. Then we have an equivalence. The Abel's problem has an algebraic solution if and only if, in fact, the sequence p to the n minus d, where d is in fact the integer which occurs in the power of the Puiseux expansion, and we ask this to have the Gauss property, so it satisfies Gauss congruences for all large enough prime numbers. Okay. Okay, so I will give some remarks, and first I just rewrite the results in compact form. So you have eta of x, which has the following expansion, and we ask the Pn to be in Q, and delta is a complex number, okay? And so we have the equivalence between a non-zero algebraic solution to the differential equation and the Gauss property Gp for the sequence, okay? So first remark is that, as I said, you can formulate something at infinity. It's not a problem. And in fact, you can just focus on the case on an expansion at 0, because you can always make the following change of variable, x plus delta. And you see that it's still algebraic, okay? And in fact, it leads to an equivalent problem of Abel. So you can focus on delta equal to 0. And in the particular case, or when d is equal to 1, so eta has a Laurent expansion at delta, okay? In fact, the prime numbers p for which since d is equal to 1, pn minus d becomes pn minus 1, and the prime numbers p for which this sequence satisfies Gauss congruences can be guessed from the distant constant of y. What I want to say is that you have an algebraic function eta, you look at the Abel's problem, and you know that y, you have a non-zero algebraic solution y. Okay. So since y is algebraic, you have a theorem of Eisenstein, okay? We say that you will have a constant, okay? So that so non-zero, so that this series has integer coefficients. So we work over Q, okay? And now this constant is adjacent constant. And in fact, so you want to know, this thing just ensures that you have Gauss congruences for large P, but you want to control for which P it occurs. And in fact, this prime P are just the one that does not divide the adjacent constant n. But you have d equal 1 as a restriction. Okay. So this criterion is useful to prove algebraicity via congruences. Okay. So your question is about Abel's problem, and you prefer to prove congruences. So the first question is maybe congruences are not that easy to prove, but in fact, in the hypergeometric case, congruences are quite manageable, okay? Because the particular shape of hypergeometric series is multiplicative, and so congruences are not that bad. So it turns out that in fact it allows us to prove Golyshev's prediction, as we will see later. But it could also be useful to prove Gauss congruences via algebraicity. Okay, so the first naive example is to try to recover the result of Gauss, and you start with eta, which is r over 1 minus rx. Then you see that you have the following solution, y, which is rational, so algebraic. By the criterion, it says that in fact you have Gauss congruences, and the thing is that if r is an integer, y has already integer coefficient as a power series. So its adjacent constant is 1, okay? So by the above remark, when d equal 1, which is the case there, in fact, we know that it has Gauss congruences for all prime which not divide 1, so all primes, okay? And we retrieve Gauss result. And you have another application, which is in our article about the number of bridge in random walks, and where it was already known that they are algebraic, and we deduce from this Gauss congruences for these sequences. Okay. So let's see how to apply the arithmetic criterion to the hypergeometric case. So I give another definition. So we say that a hypergeometric series is globally bounded if it has a positive radius of convergence, and if you can find something like an adjacent constant for f, okay, so it is not a priori algebraic, but you can rescale f so that it has integer coefficient. Then we have the following criterion for hypergeometric series. So you start with an hypergeometric series which is non-polynomial, okay, and globally bounded, okay. So non-polynomial, you just ask that the parameter alpha at the numerator are not negative integer. Then you have the following assertion which are equivalent. The sequence of coefficient of x times f has the Gauss property. So Gauss congruences for almost all p, if and only if f is factorial. Okay. So when you know this, in addition, if you know that f is factorial, then you know that there is a rescaling of f alpha beta c of x, which is equal to the generating series of factorial ratio. Okay, and then we prove that this series satisfies Gauss congruences for all prime p. Okay, so this is this result that allow us, in combination with arithmetic criterion, to prove a Golyshev prediction.
Maybe
So,
one question. Being factorial, one can implement it in the computer. Is there any algorithm?
Yeah, we can. Yeah, it's not hard because, in fact, you can easily, compute this and write down an algorithm. Yeah.
Okay.
Yeah, which take the alphas and betas as input. Okay. In fact, it's just some symmetry into the sequence, into the parameters alpha, and independently the same symmetry in the parameters beta. And okay. Okay, so just as a remark, every algebraic function series, hypergeometric series, is globally bounded. This is in fact the Eisenstein criterion. Okay. But in fact, this criterion is not restricted to algebraic series. So you can also apply it to transcendental hypergeometric function. Okay. So it essentially says that in fact the Gauss property occurs if and only if you are factorial. Okay. So the first part of Golishev's prediction, so follow from this criterion. So how? If we use the arithmetic criterion we said before, and in fact we know that Abel's problem has an algebraic solution if and only if the series eta has a Gauss property. So in the case of Golishev's prediction, the series eta is x times, so this is this one. Okay. And now we know that if f is factorial, by its sense, that in fact this has the Gauss property, and so Abel's problem has an algebraic solution. Okay. So we just focus now on this hypergeometric criterion first, and then I will give a sketch of proof of the general criterion, the arithmetic one. So I start with the hypergeometric function, which is non-polynomial and globally bounded. So I write the sequence of its coefficients like this, okay? And I let D be the least common denominator of the rational numbers of the alpha and beta. Okay, so one can prove the following congruence. So here there is no restriction about symmetry in the alpha and beta, and f is not assumed to be factorial. And it's why I call this an almost Gauss congruences for large P. Okay, so for all non-negative integer s and every relative integer m, you can prove the following congruence. So as you see, it really looks like Gauss congruences, but in fact, in Gauss congruences, you will not have the thing in pink, so you don't have this. Okay. If there we just have q alpha beta here, it will be exactly Gauss congruences for the sequence there. Okay. But here we have some perturbation, and we have these congruences which occurs. So with some k, this k is easy to compute. This is just an integer such as k times p is 1 mod d. Okay, d is parameter fixed by the parameter alpha and beta. Okay, and then we have this notation, the angle of x, which is the fractional part of x if it is not an integer. So almost it is often this, but in fact this is like the fractional part, but just when it is 0, we send it to 1. Okay, so if x is an integer, then angle of x is 1. Okay. So we see that so we can prove this congruence. Okay, it is close to Gauss congruence, but not. And this is exactly the things that will force the hypergeometric series to be factorial. Okay, so let's take an example. If you take alpha is 1/3, 1/3, and beta 1/2, 1, you take the prime p11. Then if you make the calculation, you see that g is 6, okay, and p is 5 modulo 6, okay. So you can find an inverse of p, and this is again k is equal to 5. So now you have the first term, okay, that doesn't move, okay, and there you have to calculate this, okay, which is there, okay, and there. So if you do the calculation, you see that the parameter beta doesn't move, and in fact it changes the parameter alpha, and you move from 1/3 to 2/3, okay, and now you have these congruences. The point is that if now you will ask for Q alpha beta for this series to also have Gauss congruences, it will have two congruences. So this one and Gauss congruences, and in fact it will force this term to be congruent as the same when you replace 2/3 by 1/3. Okay, and it will in fact, we will see later, it will force too much symmetry and exactly the fact of being factorial. So I just rewrite the congruence, which solves all the time, okay? And now we have an equivalence, which is the original sequence has the Gauss property, and in fact, the alpha are equal to k alpha. So there is something which is hidden. So there is the first thing is obviously the proof of the congruence. Okay, I don't prove this here because it's a bit cumbersome. This one, and then, as I said, if you have Gauss property and these congruences, in fact, you naively you tend to believe that it forces this to be equal to alpha and this to be equal to beta, and in fact this is true. You can prove this. Okay. So now that you have this, so we are here. Alpha has to be k alpha and beta to be k beta after the map angle, and this is true for all k coprime to d, and it forces in fact too much symmetries in alpha and beta, and it follows that in fact f alpha beta is factorial. So this is a sketch of the hypergeometric case. And now I go for a sketch of the proof of the arithmetic criterion. So this is in 3 steps. And the first step, we focus on an easy case. We look at the point 0. We take d equal 1, and the sequence in the expansion, the Puiseux expansion of eta, are integers. So we look at an algebraic function, an expansion eta, which is a Laurent expansion like this with integer coefficient. So in this particular case, we have the following formula for y. Okay, so this is x to the p and this minus 1. Okay, an exponential of this power series. And we will use, which is the main tool of the criterion, the following result of the Chudnovskys. you take a power series with rational coefficient, and you ask that it has an existent constant, so you can rescale it to a power series with integer coefficient for some non-zero rational number. Then, if the logarithmic derivative of y is algebraic, then y is also algebraic. Okay. So here, for simplicity, we assume that the coefficient p minus 1 is non-negative, so that we have y which is a power series with a rational coefficient, and which fulfills the assumption of the Chinosky's theorem. So, since we already know that eta is algebraic, we already know that the logarithmic derivative of y is algebraic. Okay. So in fact, we have to prove by the Chinosky theorem that the following assertions are equivalent. So you can rescale y into a power series with integer coefficients if and only if the sequence p to the n minus 1, so n minus 1 because here g is equal to 1, has the Gauss property. Okay. So now, thanks to the theorem, we focus on this equivalence. Okay, so maybe just okay, we see that after the theorem of the Chinosky, we jump to something which is really arithmetic. Okay, and we want to prove with congruences that in fact something about denominator of the coefficient of y. And the first observation is that since we know that the coefficient of the sequence Pn are integer, it is easy to prove that for every prime p, if you put p squared, so you replace x by p squared times x, in fact, it gives you a power series with coefficient whose denominator is not divisible by p. And it really just comes from the formula above of y that you can expand and look at denominators, and you see that in fact p square is sufficient to cancel the denominators. Okay, so the point is that it's good news because in fact you can easily cancel the prime as the denominator of y, but of course you want to do this just for finitely many primes, so you can't construct a constant with infinitely many primes, so you have to ensure that in fact y has already p integral coefficient for almost all prime p, and then it will be sufficient. So due to this observation, we have now the following equivalence, that you have an existent constant for y if and only if y has already p integral coefficient for large Gauss prime p. Okay. Okay. And now this is something that is handled by the Dunant-Edwards lemma. So this is a lemma about p integrality of exponential, and it is really useful in the sense that if you're studying p integrality of exponential of a series, you will use the Dunant-Edwards lemma because in fact it cancels the exponential, and you can now look at another congruence, but just on the series and not the exponential of the series. So it is really more easy to investigate, okay? Because when you want to expand exponential of s, there is a lot of calculation. So okay, what says this lemma? So you start with a power series with rational coefficient and which has no constant term, and you take p prime number. Okay, then you have an equivalence. The exponential of s has p integral coefficient if and only if you have this congruence, but as you see, exponential disappeared. So this is s of x to the p minus p times s of x, which has coefficient which are divisible by p. Okay. Okay, so it has denominator, but denominator which are not divisible by p. Okay, so it's the periodic variation, at least one. Okay. So if we recall the formula for y, we have this formula. So now s of x in the données de leur lemma is in pink, and it is now in pink in the formula of y. And so we have just to focus on this. And I recall that we have this. So now this is the thing we want to know, if there is an existent constant or not. And then now it is equivalent to this. By the données de leur lemma, now it is equivalent to this condition applied with s of x is equal to this. Okay, so we will write down this. Okay, and just this is I rewrite the données de leur lemma, and we have an equivalence. So exponential of s of x is as p integral coefficient, if and only if you write down the thing. So if you write down these congruences with this, you will exactly find Gauss congruences, in fact, and so you directly obtain the desired equivalence. Okay, and this proves steps 1. Okay, the equivalence with the Gauss congruences. And what is really funny in this proof is that, in fact, you start as usual with easy cases to see if your proof works well. So you look at d equal 1 and you start with a sequence p with of integers. And it turns out that when you prove this step, in fact, you can use this step to again prove, in fact, second step, still with d equal 1, but the sequence p now are rational number, and it is really quite direct. And then that you have these things, there is even more simple. You can generalize this to an arbitrary d, and so in fact you obtain the whole case. Okay. So thank you for your attention.
Okay, thank you.